Brouwer's fixed point theorem states that every continuous function f from S to S, where S is a d-dimensional simplex, has a fixed point. And a fixed point is a point x from S for which f of x is equal to x. So we have a function that takes points from the simplex, say a point here, and maps it to a point on the simplex, say here. And then takes some other point from the simplex and maps it to this point here. And then maybe this point over there is mapped to this point. And then there might be points that are mapped onto themselves, and that's what we call a fixed point. And Brouwer's fixed point theorem just states that any continuous function must have a fixed point like this. And we now want to prove this fixed point theorem. Sperner's lemma and Brouwer's fixed point theorem superficially look like two very different statements. But in fact, Brouwer's fixed point theorem can be viewed as a continuous version of Sperner's lemma. And so indeed, we will heavily rely on Sperner's lemma in our proof of Brouwer's fixed point theorem. This is the reason why I told you about Sperner's lemma in the first place. I want to start with the proof of Brouwer's fixed point theorem for the one-dimensional case to explain some of the main ideas. And then after that, I will discuss the two-dimensional case. For the one-dimensional case, the simplex, the one-dimensional simplex, is just a line. Say it's a line containing the real numbers between 0 and 1. And so if we have a function from the interval 0, 1 to the interval 0, 1, we can plot this function. It might look something like this. Now, what will be interesting is to look at the diagonal in this graph. So we draw a line from the origin to the point 1, 1. And now what happens is that the points where the plot of the function f crosses that diagonal, those are exactly the fixed points of the function f. And now we can already see why these fixed points must exist. Because if I have a continuous function, so I have this line that I draw here, then it must touch or cross this diagonal. Formally, this follows from the intermediate value theorem, but I think even intuitively this is quite clear. And now all of these touch or crossing points are fixed points of the function. And so a fixed point must exist. Okay, I now want to repeat this proof, but formulate it in a slightly different way. And it will be a bit more complicated. But while doing this, I will introduce some ideas that can then be used to generalize this proof idea to higher dimensions. Okay, so what we do is the following. We color all the points on this one simplex, on this line. So all these points between 0 and 1 we will color using two colors, say red and blue. And we will use the following rules. So a point x from the simplex gets the color red if f of x is strictly bigger than x. And we color a point blue if f of x is strictly smaller than x. And if f doesn't have a fixed point, then one of those two conditions must be true. So each point would get a color. And if f does have a fixed point, there's nothing left to prove. We're already done. So we can just assume that every point now gets a color like this. And now we subdivide this simplex into smaller intervals. Now this point at the very left, the leftmost point at 0, clearly has the color red, right? Because f of x cannot possibly be smaller than 0. And the rightmost endpoint must be blue, right? Because f of x cannot be larger than 1. And so we have red at the very left and blue at the very right. So there must be some segment, some edge in the middle somewhere, where one endpoint is red and the other one is blue. Right? So we must have a red-blue edge. Very much like in the proof of Sperner's lemma. We've already discussed this. Okay, so no matter how I subdivide the simplex, I always can find such a red-blue edge. Now, what we do is we make a sequence of finer and finer subdivision of this simplex, such that the length of the edges gets smaller and smaller, and in the limit approaches 0. Okay, so we add more and more intermediate points here. Now, consider a sequence of the red endpoints of a red-blue edge in each subdivision. This sequence of red points must converge to a point z. Actually, this is not completely true, but it must have a subsequence which converges to a point z. Formally, this follows from the Bolzano-Weierstrass theorem. For this z, it must be that f of z is greater or equal to z. Right? All of those points in the sequence were red points, so for each of them we had f of x is bigger than x. And so for the limit point, because f is a continuous function, it must be that f of z is greater or equal to z. But now consider the sequence of the corresponding blue points. And this must converge to the same point z, because the length of the edge tends to 0. So the red and the blue point get closer and closer together. And so for a similar reason as before, it must also be true that f of z is less or equal to z. But now we have f of z is greater or equal to z and also smaller or equal to z. And so we conclude that f of z must actually be equal to z. And therefore z is a fixed point of the function f. Okay, so this was a slightly more complicated proof for one dimension. But if you understood those arguments, you will also easily understand the arguments that we need for 2 dimensions. Okay, so for the proof for 2 dimensions, first of all, we refer to the points in the triangle with barycentric coordinates. So a point is specified by 3 numbers, x1, x2, and x3. All of those are non-negative, and they must sum up to 1. And then the 3 corners of the triangle correspond to the coordinates 1, 0, 0, and 0, 1, 0, and 0, 0, 1. And the way you should think about this is that, for example, the first coordinate, x1, grows with the distance of the point to this upper right facet. Right? And then the second coordinate, for example, would grow as you move further away from the bottom line of this triangle. So that's how barycentric coordinates work. Okay, so now we color all the points in this triangle. And we have coloring rules similar to the one-dimensional case. Specifically, a point x, consisting of the coordinates x1, x2, and x3, which is mapped to f of x, which is a point that consists of the coordinates y1, y2, and y3, is colored red if x1 is strictly bigger than y1. So the first coordinate gets strictly smaller when we apply the function. And otherwise, it's colored blue if the second coordinate gets strictly smaller if we apply the function. So if x1 is less or equal y1, and if x2 is bigger than y2. And we color it green if x1 is less or equal to y1, and x2 is less or equal to y2, and x3 is strictly bigger than y3. So that's our three colors. And now, if the function f does not have a fixed point, once again, every point in the triangle actually gets a color when we apply these rules. You can convince yourself of this very quickly. So if this is not the case, then it must be that x1 is less or equal y1, otherwise it would be red. X2 must be less or equal y2, otherwise we would color then blue. And then also x3 is less or equal y3, otherwise it would be colored green. But we also know that the three coordinates have to sum up to 1. And so the only possibility now is that x1 is actually equal to y1, and x2 is equal to y2, and x3 is equal to y3. And that means this particular x would be a fixed point. So if we don't have a fixed point, then every point receives a color if we follow those rules. Another observation is that this coloring is valid in the sense of Sperner's lemma. So, for example, if we look at a point on the upper right facet of this triangle, then all points on that facet have the first coordinate equal to 0. And therefore, it cannot be that any of those points are colored red, because x1 is 0 there, and it cannot possibly be that 0 is strictly bigger than y1, because y1 has to be non-negative. And you can make similar arguments about the three corners and about the other facets. Okay, so now we have this big triangle, this two-dimensional simplex, and we can subdivide it into smaller and smaller triangles. So again, we create a sequence of finer and finer subdivisions. And we do this in such a way that the size of these small triangles, the diameter of those small triangles, as we go along the sequence, actually goes to 0. So we add more and more smaller and smaller triangles, and the diameter tends to 0. We know from Sperner's lemma that each of those subdivisions in this sequence must have a trichromatic triangle in it. So there must be a small triangle in each of those subdivisions that has all three colors at the three corners. And then again, there must be a subsequence of such triangles, this trichromatic triangles, that converges. And specifically the three corners will all converge to the same point z, because the diameter of the triangle gets to 0, so all the three corners must converge to the same point. The red corners, if you follow the red corners in the sequence, they converge to z. And for the red corners, we know that the first coordinate gets smaller when we apply the function, so the same must be true for the limit point, because the function is continuous. So in the limit, we have that z1 is greater or equal to the first coordinate of f of z. And then we can follow all the blue corners in this subsequence. And those also converge to z. And from that we conclude that z2 must be greater or equal to the second coordinate of f of z. And then we follow the green corners, and we get that z3 must be greater or equal to the third coordinate of z3. So combining all of those things, together with the fact that we know that all the coordinates have to sum up to 1 always, we get that z1 is in fact equal to the first coordinate of fz, z2 is equal to the second coordinate of f of z, and z3 is equal to the third coordinate of f of z. And what it just means is that z is equal to f of z. And so z is a fixed point. Okay, so that finishes the proof for 2 dimensions. I'm not going to prove the theorem for higher dimensions, although the statement is still true. But you can easily think about this yourself if you want. Basically, the proof just is exactly the same for higher dimensions. You just need a higher dimensional version of Sperner's lemma. So we can generalize Sperner's lemma to higher dimensions. Then we would need more colors, of course. For each dimension we add, we need one more color. And then you can use this higher dimensional version of Sperner's lemma to prove the higher dimensional versions of Brouwer's fixed point theorem. The second remark I have is that Brouwer's fixed point theorem is still true if we replace this simplex S by any other convex compact set, or indeed any set that is topologically equivalent to a simplex. And by the way, compact just means bounded and closed. The reason that this still works, as long as the set is topologically equivalent to a simplex, is that roughly speaking, we can just deform the set and with it the function back into a simplex form. And then we can apply the theorem. But be careful, because the theorem in general is not true for arbitrary non-convex or non-compact sets.